this seminar is slightly different. We are making an effort to join a few of the seminars we have that include INPA in the organization. And today we're having our usual seminar with joint with COMEA. So that also implies another difference, that we're gonna have another seminar that is COMEA only after this one. So everyone who wants to stay for longer is very welcome. And today we have Marcelo Hilario from the Federal University here at Minas Gerais, who's gonna talk about percolation with directional disorder. So please, Marcelo.
Thank you, Augusto. It's a pleasure to speak in this joint seminar, COMEA and the usual seminar on Wednesdays. And so thank you, and Eulalia, Claudio, Pablo for the invitation. And my title, I think I gave a title with the cubic lattice standing there, but maybe I will not talk too much about the cubic lattice, but more about the square lattice. Well, we'll see. So since this is joint with this COMEA seminar, to stay in the safe side, I will start like very basically recalling what percolation is. By the way, Augusto, how much time do I have? Well, okay. I'm assuming I have like 50 minutes or something like
50 minutes,
that.
yes, Marcelo, you have 50. Augusto, you can't hear, you can't, you're mute.
So, okay, so let me start.
Sorry, I was mute.
So as I was saying, let me start in the safe side. So recalling what's a percolation process. So giving a lattice, let's say the square lattice, I will assign random variable 1 or 0 to each edge of this lattice. And whenever you see a 1, I will think that the edge is open and a 0 closed or present or removed. And then this gives rise to a random subset of this lattice. And we can see a picture here. And we are interested in studying connectivity properties of this random subset, like size of clusters and whether or not one given point is connected to the boundary of the boxes or quantities similar to those. Okay, so the simplest thing that you can do is to assign the states of the edges independently with the same probability. So let's say P. And here I prepared three pictures with different values of P. And you see on the left, you have low connectivity. The thing is essentially all disconnected. While in the right, you have something much more compact. So you see you have a robust structure. So you have crossings from one side to the other, from bottom to down, from bottom to up. And in the middle, you have something in between that in principle may look a little bit like the one in the right. But if you check carefully, you're going to see that it's very fragile in the sense that if you if you just switch the state of some few edges or maybe one edge, you're going to change the fact, for instance, that there is a crossing from one side to the other. Okay, so this three kinds of behavior divides the phase state in three different phases. The left one very disconnected, and you see here I have painted the largest components in the boxes here. So here you see all components are very small if compared to the size of the box. On the right, you have a giant component that takes almost everything. And in between, you have this thing that wants to become giant component, but it's still a little bit, it doesn't take too much of the volume of the box. So some quantities that we would like to study is, for instance, the probability that the origin belongs to this giant component. And if you increase this value of P, the parameter, then one time you want to keep track of the first time when this quantity starts to be positive. So this is the critical point, should be this value of P that gives this picture in the middle. And you also want to keep track of other quantities, like for instance, the probability that the origin connects up to distance n is what's in the right side here. And it's well known that you have three different phases: the subcritical phase, the supercritical phase, and the critical phase just in the middle, separating these two other phases. And here you have an infinite cluster that is unique. And on the left, in the subcritical phase, you only have finite components. And here I want just to call your attention that in the subcritical phase, the probability that a given point in the bulk is connected up to the boundary of the box decays exponentially fast in the size of the box. And same thing here, if you want to connect to distance n, but not touch the giant component, then this probability also decays very fast. And in the middle, you have this signature of the phase transition that it's the power law decay. It's just expected to be found in the critical phase and not in the subcritical and the supercritical phase. All right, so my goal here is to talk about some more exotic kind of percolation, where we introduce either a strong correlation between the edges or the sides of the lattice, or we just let P change, the parameter change from column to column or from plane to plane in this lattice, or maybe we decide to pass to a dilute lattice. So we select some columns at random and just drill through these columns and get a random lattice, which behaves like a random environment. And on top of that, then you can run your percolation process. And I'll try to show towards the end some techniques that we use to control these processes. So we have to control both the environment and the percolation on top of this environment. And the technique that we're going to use is renormalization. All right, so to start with, let me start with a model that I really enjoy, and I've been working with this one since 10 years ago. And so imagine that you have this cube made of wood, and you decide to drill through each face to the opposite side with some probability that can depend on the direction, all right? So you remove straight lines instead of single bits in the in your media there. And this was first introduced long ago by Cantor, and then studied with co-authors, including Augusto and Nuno, who are in the audience in this paper here. And so what we know about this model here. So first of all, the math definition, I just mentioned, you remove parallel lines in the infinite lattice with probability 1 minus P, depending on the direction. Okay, so I'll keep one PI for each one of the directions. And the goal is to study these connectivity properties of what remains. So not the set of lines, but what's not touched by these removed lines. So a theorem that we proved with Vladas a while ago, and was published only in 2019, is that if one of the parameters is subcritical, but for the usual site percolation process, then already the probability that the one given site connects to infinity is 0. And so what's happening here, if you drill too much in one direction, then you are already doomed, because you're going to separate your original lattice into cigar-shaped, like cylinder-shaped regions. Then you're basically one-dimensional, and then you're going to get killed by the drilling coming through the other directions. And on the other side, if you take all the parameters large enough, then you percolate. So no surprise here, it's a usual phase transition, right? And here I have a picture of a simulation in the paper with Nuno and Augusto and others. Here, the simulation is for d equals to 3, and all parameters, so you're drilling in all directions with the same intensity. And then we found a phase transition around this value here, which is strictly bigger than the critical point for site percolation in Z2, which should be something like 0.59. So here you see this pi is the probability of crossing from bottom to top in a box, and you have something happening around this value here. The probability goes very quickly from 0 to 1 around here as you increase the side of the box. All right. So this is just the phase transition for this model. But what I think is interesting is related to the sharpness of the phase transition. Because if you recall, for Bernoulli percolation, you have exponential decay on both sides, and something different can only happen in exactly on the critical point. And here the picture is much more complicated, because we have the following. If you drill too much in a few directions, let's say 2 directions, then you have exponential decay. All right. On the other side, if all the parameters are sufficiently large, then let's say all but one, then the probability that you connect up to distance n, but not to the giant component, cannot decay exponentially fast. It can decay at most as a power law. So it means that if you take, like now, P1, who doesn't appear here, very small, then you already disconnect everything. Then this part here is not necessary inside the probability. And you see, you are within the disconnected phase, and you don't have exponential decay. So the picture is a bit more complicated in this case. So you see, you have some kind of extended phase here. Let's say this picture is for d equal 3, and all parameters equal to p. So I'm drilling with same intensity in the 3 directions. And what we have here is that we have a phase that it's very disconnected. You have this exponential decay. Then you have a phase where you have a giant connected component. And in this region here, you have at least a lower bound that it's a power law. And it's an open problem from the math point of view to prove that this gap really exists. So I mean that this quantity P star, the critical point, is strictly bigger than PC of Z2 in dimension 3. And but it's clear from the simulations, as I showed in the last slide, that this gap really exists. So you have this intermediate phase, and this is what I consider to be very nice in this model. And I think I included this model mostly because it really illustrates that when you're dealing with these strong correlations along lines, then the nature of the phase transition can change substantially. All right, so let me now go back to the square lattice. And another way that you can introduce lower dimensional disorder is by selecting some columns, let's say this set of columns that I will call B right now. So they are just marked in different color here. And I will decide whether or not edge is open depending on the location of this edge. So if it lies on one of these selected columns, then I open with probability Q. Otherwise, if it lies in a blue column here or it's a horizontal one, then I open with probability P. So now I have these two parameters. So this model has these inhomogeneities. And now, once again, if you quench your disorder, so you have your condition on these lines, then the state of edges are going to be independent, but inhomogeneous. Now, if you average on the disorder, then you have infinite range dependencies that just spread along this vertical direction. So there are several well-known cases, and two of them degenerate. Let's say that I only choose a single column to change the value of the parameter. And in this single column, I will, let's say that I start at the critical phase, and then I give a boost here. I just increase a little bit the parameter in this one single line. And it's not enough for create an infinite cluster. So regardless of how much you try, as long as you don't hit one, of course, you're not going to be able to create an infinite component. This is a result from Zhang in the 90s. On the other extreme, you can think, okay, let me just enhance the parameter on every line, every vertical line. Now it's a line that it's painted, like in the previous slide. And then something interesting happens. If you increase this parameter by a bit in the vertical lines, you can decrease outside in the horizontal lines. And if you increase faster than you decrease, then this is already enough for you to create an infinite cluster. So this result is due to Kasten in the 80s. And much more interesting is to think of what happens in between. And there is this technique due to Eisenman and Grimmett that allows us to study this type of problems when you have these columns, let's say periodically spaced in the lattice. And what this formula here says is that, suppose that if you increase the, you can increase the parameters in this set of lines B and decrease in the outside, not too fast, then you still percolate. So it's similar to the previous one, but now you don't have, maybe you have to decrease much slower outside the vertical lines on B, because you have to account that this enhancement is being done in maybe very sparse set of columns. So, so this says that if you increase, again, from the critical point, if you give a boost in these lines, you make it better for percolation in these lines, then you can even decrease outside with a certain delta that is going to depend on epsilon and on the set B, and you are going to have percolation. All right, so of course, when we think of disorder, we may pick this set of lines at random. So this is what is more interesting, and the problem with this technique of Eisenman agreement is that it usually breaks down when you choose this set B with lines that can be very, very, very far away. So if you're just tossing coins in order to decide whether or not a column is going to be enhanced, then maybe you're going to find very large regions where you don't enhance anything. And this technique, the way it is stated in their paper, is completely breaks down in this case. So we consider this case when the spacing between these columns are given by a geometric random variable. And what we got is that the same result, okay? Now, regardless of the density of the lines and of the amount that you enhance in these lines in B, you can still decrease a little bit outside and have percolation. So in words, even when good is just slightly good, it's just C plus epsilon, and it's very, very rare. So if this rho is very small, if you do not do too much damage here, you should not decrease too much the parameter outside, then percolation will still take place. And there are some other results in the same direction, and I will not be fair to lots of people who have worked on that same kind of problems. But I just wanted to mention two works in oriented percolation or in the contact process in the same spirit. So these are the works of Bramson, Duhet, and Schoeman, and Kesten, Sidoravicius, and Varis. And what I think is interesting here is that, so the setting is different in all of these papers, but what's more interesting is that the order that you change the parameters give different kind of results. And so in this paper, Bramson, Duhet, and Schoeman, they consider the contact process, and they have this good lines in the direction of time. So it's oriented in the direction of good lines. And let us assume that the other lines are very, very bad. And these good lines are rare. If you make these good lines sufficiently good enough, then the contact process still survives. On the other hand, Kesten, Sidoravicius, and Varis, they studied oriented percolation, which is similar to contact process, discrete version, but now with the bad lines transversal to the direction of time. So it's much more complicated problem in this sense. But the qualitative picture here is that if bad lines, even if bad lines are very bad, if good lines are just slightly good and bad lines are very, very rare, then these bad lines are not going to be able to disrupt percolation, even though they are perpendicular to the time direction. And our work from the previous slide, as I mentioned, the order that we pick the parameters is different. So if good lines are just slightly good and very rare, then if bad lines are not too bad, they cannot disrupt percolation. So these are the three kind of problems that you can try to study in this setting of good lines and the bad lines transversal to the time or parallel to time or even non-oriented in our case. All right. So a very similar kind of problem is when we now are back to the square lattice and we try to dilute this lattice. So if I just drill like in the cube, in the works in line, in this drilling percolation, and I drill through the sides and then try to do side percolation, then it's not going to be good because I will just disconnect the lattice. So the nicest thing to do here is to just delete edges at random in some locations in your lattice. But you see, even if I delete all this column here, I can still connect just going around. So I will pick one variable, let's say integer valued, and prepare lots of copies of this random variable independently. And I will remove I will just keep the ones that are spaced by these random variables here and remove vertical edges in between. So this gives rise to one-dimensional random environment here of columns, which I can mark with this x0, x1, and so on. And outside this, I will just delete the columns. So in what remains from my lattice, I will declare each side open or closed with probability P. And you see, now you can just replace one horizontal edge like this one by a longer edge whose probability of being open is P squared, because you pay P for opening this one and P for opening this one. Then to connect from this side to this one, you have P squared. And this square comes from the fact that this random variable here assumes the value 2. So what I really want to do is to pass to the continuum. Let's say now every random variable is allowed, positive random variable is allowed regardless whether or not it's integer valued. And I will open horizontal edges with the probability P to the side. So I'll just repeat this in the continuum. All right. So edges are just open. Horizontal edges are opened according to the value that this psi random variable assumes there. Is it clear, the model? In case anyone has some doubt, I'm available in the, I can read the chat, so you can just post. So I think it's clear the setting now, right? So the question is like, does phase transition always occur in the setting? And if so, how does it depend on the law of these random variables that you are using for stretching the model? So this has been considered in other works, and in this work of Jonasson, Mossel, and Paris, they consider stretching in ZD, so D dimensions, and in all directions, not only in one direction like here. And also in the work of Hoffman in 2005, they consider two dimensions only. And in all these works here, the psi random variable have to be geometric, all right? So we want to let go from this geometric setting where the spacing is geometric, and really study how amount of stretching or the moments of this random variable interfere in the presence or not of percolation, right? So our theorem, together with Augusto, Remy Sanchez, and Marcos Vinicius Sá, is the following one. It says that if the tail of this stretching random variable decays sufficiently fast, so meaning that this moment of order 1 plus epsilon is finite, then usual phase transition occurs in some sense. So if you have P larger than a critical value, then you have an infinite cluster, almost sure. And this for all realizations of your disorder, almost all. Now, if you take P smaller than this critical point, then probability that the origin connects to infinity is 0. So you really have a classical phase transition in the sense that you have a disconnected phase and a connected phase. But sharpness, exponential decay shouldn't take place in all the subcritical phase. I will not come to this detail. What's interesting is that now if you stretch too much, then you completely destroy the phase transition, in the sense that it doesn't matter how large you make P in the interval 0, 1, you are certain that percolation is not going to take place. So this can be improved to first moment, but so here, if first moment is infinite, then we know how to do it and show that percolation doesn't occur. But on top here, we don't have any substantial improvement from this condition, meaning that maybe with some effort we can put something better than this, but we cannot get to first moment. So an open problem here, which I think it's interesting, is to determine whether or not this change of behavior takes place exactly when first moment is finite or not. Okay, so the proof is based on a separate control of the environment. So first you try to control the environment, and then on top of the environment, you try to control percolation, and this is done usually using some kind of renormalization techniques. And in the remainder of the talk, I will try to give some hints on how to prove this result. But what I wanted to mention is that all of the results that I talked previously, they also, their proofs also go in the same direction, in the sense that you come with a renormalization argument and try to control first environment, and then once you have the environment controlled, you try to control your percolation on the top of the environment. Right, so I wanted to pick one of these problems to show the techniques that we used, and I've chosen this one. That is the last one that we worked on this topic. And let me start with the control of the environment. And usually for controlling the environment, we need something that we call a decoupling. And let's say that I will be in the setting that this size here, this side here, they all have good moments. So I really apologize for the noise. So I think it's good, right? Can I continue? So yeah, I'm sorry. Today it's really.
It's not very audible.
Okay, good. So so here I have this random variable psi, and let me assume that they are integer valued and they have good moments, meaning that when I take the 1 plus epsilon power and take expectation, this is finite. So have good moments, right? So maybe introducing some well-chosen delay here in the beginning, I can pass to a version that it's translation invariant or shift invariant in some sense. And this is good for what I will do later on. And I will assume lots of good properties of this random variable so that I can think of it as a renewal process in the integers, like here. So let's say that I mark a 1 every time I have a renewal here. So these are the positions where I will have a column in my original setting, right? So you remember in the original setting, the columns are separated by this stretching that's given by C. So if I have one column here, then I have another column here. So a sequence of zeros and ones like this just encodes all the randomness in the environment. So it's really one-dimensional disorder in this sense. And here below, I just made a drawing of the renewal chain. So here you have the time until the next renewal. So here I will renew in the next site. So I have a 0. Sorry, maybe. Yeah, here I have a renewal, so I have a 0 here. Then a 1 because I am 1 unit away from the next renewal. Now here 4 because my next renewal is here, 4 units away, and so on. So this is classical Markov renewal chain, right? And if you assume all these good moment conditions on this variable psi, then what's nice is that we have this good control on the correlation or the covariance on what happens in faraway regions on your environment. So if you take a certain event that's measurable on the configuration of the environment in a given place, and then you have a gap, say of size n, and another event that it's measurable with respect to the environment here, then they are essentially independent if this value of n is large. And this epsilon here is the same epsilon that appears in the statement of the theorem in the moment condition. So if you have good moment condition, let's say if epsilon is large enough, then this decay is even better for you. So, so this is key property of our techniques. So whenever you have this decoupling, then it's good for you to control the environment. So how we do it? So we start by picking a sequence of scales, and you should think of this as numbers that are growing very, very fast. And what I do is that I will tile the z axis here, with intervals that are given by this scale lengths, right? So I have here scale k+1, and it's tiled by blocks of the previous scale, which are tiled by blocks of the previous scale, and so on until you get to single points. And once we have this construction, these multi-scale blocks, I will define what I mean by a block in each scale being good or not. And this is a recursive definition. So what I do in the first scale, this is scale 0, I declare one box or one interval being good if I have a 1 inside, or in the original interpretation, if there is a column that is gonna pass here. So a vertical column of the lattice passing here and here, and bad otherwise. All right. So you have good, 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 and see, if I choose this L0 very large, then the probability of being good I can make as high as I want. So now I will move recursively to higher scales, and I will do so in some way that I create a kind of healing process. Even if something is bad in a higher scale, in a small scale, then maybe looking in goods in higher scales, it can become good, right? So what we do is the following. So in a higher scale, like let's say k+1, we inspect all the blocks inside, and we say that it's good if there is no two consecutive two blocks that are bad inside that are not.
Intervalos bons e intervalos ruins. Aí você usa tipo um teorema tipo.
Okay. I think someone asked the question. Did anyone? Okay, I thought I heard the question, but no, everything fine. Okay. So so here, this block here at scale k+1, this is bad because it has two bad blocks from the previous scale that are not consecutive. But this one is good because even though there are two bad blocks in the previous scale, they are not, they are consecutive ones. And here you have three, meaning that this one and the last one, they are not consecutive. So this is also labeled bad because of that. So you see, even if something has something bad in one scale, it can become good in the previous one. Sorry, in the next one. So you have this kind of procedure here. So what's the main idea then? Is that now if you define pk, the probability that one block is bad, so doesn't have much columns passing there, you have to control this quantity. And what you do is you want to show that this quantity is small. So you don't want to see bad blocks here. You want to see good blocks. So what you do is you take this block at scale k+1, and if it's bad, it's because you see at least two bad blocks inside. So this is the amount of ways that you can pick two bad blocks from scale k within scale k+1. So the square, it's because of the pair of boxes, and this is the amount of ways that you can pick a single bad block inside. And now you have to have one bad block, another bad block. This gives pk to the square if they were independent, but they are not. You have this decoupling. They are almost independent if k is large and epsilon is something positive. Right. So what you do now is that you try an induction procedure. You just try to come up with a bound here. Let's say that pk is smaller than lk to the minus alpha. You plug here and see if you get the same thing happening in the other, in the next scale, right? So here it's gonna work as soon as this alpha is of order epsilon over 2, because you have a 2 here and an epsilon here. And then this is just simple calculation. You just plug it there and see that you have this induction going on from, so you propagate from scale k to k plus 1. But in order to have this pk small in all scales, what you need to do is to have then the first scale satisfying this bound here. So what you do is you take L0 large enough. So already in the first scale, you have this bound. Then by this inequality, you're going to have for all the next scales. Okay, so this gives the control of the environment, and meaning that for every k, the probability of having a bad block at scale k decays fast. And why I call it fast, it's because this lk grows very fast. Then even if this alpha is something tiny, then this is decaying fast enough. So by Borel-Cantelli, if I inspect some large region of my environment, I will just see good stuff. All right, so I'll rely on that in the control of percolation. So if I can just take like 5 more minutes, I will now assume that I will have only good environment, and on top of good environment, I will show how to control the percolation. So here in this specific model, I have to come up with some height scales that are different from space scales. So what you should imagine here is that the height is much bigger than the width of these blocks in the lattice that I will look. So I'm back to the two-dimensional lattice to study percolation. And the heights are going to be stretched exponential, roughly speaking, if compared to the horizontal lengths of the blocks. So I have some pictures like this, and it's somehow misleading because really this should be much bigger than the horizontal scale here. And what I do is that I define horizontal and vertical crossings in these blocks here. And I want to bound this quantity here is that the probability that no crossing occur, even though the environment is good. So I will come up with some kind of induction procedure as well. So I assume that the probability that no crossings occur in scale k have very small probability, and try to propagate this bound to the next scale. And how I do this, first for horizontal crossings, since this height is much bigger than the width here, I will have many attempts to cross. So I take one of this and zoom down here, and I'll try to put together crossings of the previous scale, and they happen with overwhelmingly probability. So when the environment is good, but if the environment is good, I still allow for bad regions like this, or maybe 2 consecutive ones. And when I get to these bad regions, I'll have to cross. And the dumbest thing that you can do is try to cross straight here. So what price you pay? You pay exponential, but of minus the previous scale. So it should be exponential of minus LK here, which is not bad if compared to this, because you are choosing the scales to be LK plus 1 equal to LK to a power. So anyway, you pay this price and continue to put together these crossings. And then you have some probability of crossing here, which is good enough. And then when you take account the many attempts that you have in this disjoint strips, then you can obtain this bound in the next scale. So this is done for horizontal crossings like this. Now for vertical crossings, you try to do something very similar. So you try to put together crossings like this and try to find a crossing from bottom to top. And again, if the probability of finding a crossing like this is large enough, then you almost don't pay anything for putting together these guys. And even though they are a little bit dependent, they depend on the neighbors, you can show that the probability of crossing from bottom to top in the next scale is still high. So this is the complementary set, right? So the complementary set is small. So not having the crossing have very small probability. Okay, so this controls the crossing probability when you have good environment. And now just to finish the proof that percolation takes place when P is large, what we do is, so if K is large enough, then we only see good blocks because we have controlled the environment and showed that it behaves like this. Now, if you take P large enough and the environment is good, then these crossings are very likely to occur in every scale. Then you put together crossings of the first scale until you hit the next one. And then you put together blocks of crossings of this next one, and so on, and you build your infinite cluster like this. So you just need to start with one scale, then move to the other one, and these guys are going to connect to each other. So I think I'm running over time. So this was the proof that percolation occurs when environment has good moment conditions. I will not show the other part of the theorem, that when you stretch a lot, then you don't have percolation. And I think I will stop here. Thank you.
Thank you, Marcelo. So, are there any questions, Marcelo? So, just crossed my mind, especially because Nuno is here and brings me memories of the time we worked closer with physicists. Besides the obvious models that we know, are physicists looking into this type of inhomogeneities and trying to investigate this intermediate phase? Do you know any work in this direction?
So I think that the question is more to Nuno than to me.
Nuno pediu a palavra.
Sorry, can I ask something?
Of course.
Yeah. Well, regarding your question, I think it's always important to look to anisotropies in the system. And so people have been looking to that from different perspectives. But I have a different question. So regarding this problem that you described first, where you have a two-dimensional lattice, where you have a different probability for these vertical columns, for these specific columns that you distribute, one of the things you said is that this increase in probability along the vertical direction, what you call, I think it was epsilon, needs to be larger than delta. So the decrease in probability along the horizontal direction.
Yeah.
And so my question is that a minimum condition or a necessary one?
So yeah, this is just to this case where I enhance all vertical columns, then it's if and only if. So it's if you go faster here, then you decrease here. So if you increase faster than you decrease, then it's good enough.
Mm-hmm.
But here I'm just relying on the fact that all of these columns should be painted, these vertical ones. So you really have one parameter for vertical edges and another one for horizontal ones.
But what if you look into a density of those columns? So later you describe a case
yes.
where you have a density row.
Yeah, so if I have a density row like this, then I don't have this fine control. I only know that for all intensity of enhancement, I will have maybe a very tiny window here to decrease outside and still percolate.
Okay.
So here the argument is very perturbative in some sense that we have to choose all these boxes and run our multi-scale arguments. Then it's really perturbative here. So I can only show that there exists a delta that is small enough such that if I decrease here, I still keep percolating.
Okay, because what I had in mind is the following. If you have a certain density, what you are saying is that you have an infinite number of those columns. And so somehow you have a characteristic distance between the columns, right?
Yes.
So you no longer need that the connected path goes to infinity. He only needs to exist within a certain length scale that is the typical distance between the columns. So I was expecting that even for values of what you call delta above epsilon, provided that the characteristic length of the connected paths is larger than the distance between the columns, that you will have an infinite number of those connections between the columns when you take the infinite system, right? Does it make sense, or am I thinking wrongly at some point here in my line of thought?
Yes. Yeah, qualitatively, yes, it makes sense. So so if you look from far away here, so you should have these bands where everything is good, and in between these bands where everything is bad, right? And you try to like grow your cluster in the good bands, and so now you're going to have exponential decay in between, right? But if you have a very high density of connections, so in these good bands, then you have hope that very often you're going to cross the bad regions. But the pain here is to really have this qualitative trade-off between what you gain in the good regions, in the good bands, and what you lose in the bad ones. And so I think that what you described from the physics point of view, it's I think completely clear, but somehow from the math point of view, for us, it's a bit difficult to take all these scales in account, to account for all these scales and really prove it in a non-perturbative way. So probably this can be done, but I don't know how to control it as finely as you want. Like really, you want to give a much better control than what I have here. But yeah, you should be right.
Okay, thank you very much, Mike.
Are there
It's very
more
interesting
questions?
question, by the way.
Okay, if not, let's thank Marcelo again.
Okay, thank you.
Thank you, Marcel. Very nice talk. So, as I said, this is an experiment, so we are still learning. We had a slight mismatch in the time schedule because the length of the two seminars is different. So, in principle, Nuno's seminar shouldn't start in sequence. We should have a break, but I think the break predicted in the poster is a bit too large because Marcelo's talk was shorter because it was joint. So should we make a shorter break, perhaps? And if anyone wants to continue in the chat, we welcome to, we can socialize a bit. And anyone who wants to leave and join later or has a commitment cannot join. See you next time. So just before people who may not stay leave, I would like to say that we continue on next Wednesday with, I think next Wednesday is Perla, if I'm not mistaken, Perla Susi.
No, Chris Thursday.
Oh,
Chris
yeah.
Thursday.
Yeah, thank you. So next week we continue with Kilton Bursey from Washington, and then Perla the week after. So thanks everyone. I think we should probably interrupt the live streaming from IMPA and continue the one from UFRJ's